Thursday, we take our own, like, sample.
Oh no.
Or we could have a final.
Wait, so,
It's not a sample.
it's like a, it's not.
We've been doing like 2 chapters in a unit. This next unit, we are actually going to do 3 chapters, chapters 7, 8, and 9, but we are only covering 2 sections out of each chapter. So we're kind of picking a few key things. The setup for this unit is going to be a little bit different. You will not need your textbook at all unless you want it. So for each chapter, which is only 2 sections, I have your notes handout, and then I will give you an assignment packet for the chapter, essentially, and it's broken down by section. So that's kind of the plan. We are going to do chapter 7 this week, so we only have 3 days. So today we'll do 7-1, tomorrow we'll do 7-2, and then Wednesday we're just going to review the 2 of them, and probably give you guys time to work on homework in class so you can have it done and not have to take it home over the weekend. So that is my plan. We are starting with the normal distribution. We're looking at some different probability distributions. So remember, in chapter 6, we talked about what a probability distribution was, right? Basically listing your outcomes and their probabilities. We talked about the binomial distribution being one specific type of probability distribution. But now we're going to look at another one, what's called the normal distribution. With this, we have the probability density function. It's called a PDF. It's an equation that's used to find probabilities of continuous random variables. So here's what's different. All the probabilities we've done so far have been discrete. We could list all the possible answers. In the binomial, there's only a yes or a no. But in a normal distribution, we have continuous data. So it might be the amount of time it takes to complete something, or the weight of an object, or something like that, where we can't list every possible value and its probability. However, when we're looking at them, we'll look at graphs, and when we're talking about it, the total area under the graph, which is like your total probability, has to be 1. Okay, because probability always adds up to 1. And the higher the graph must always be greater than or equal to 0, because can you have a negative probability? No. So same rules that we had before. We're just looking at continuous data. We are going to just touch on the uniform distribution first. Not one we see very often, but it is possible. So in a uniform distribution, each outcome is equally likely. So for example, United Parcel Service is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Let X represent the time from 10 a.m. when the delivery is supposed to take place. So X equals 0 would be at 10, 10:01 would be when X is 1, 10:02 would be when X is 2, so X is the number of minutes past 10 o'clock. Draw a graph of the distribution if each outcome is equally likely. Alright, so we were going to graph it. We have our X, which in this case is our minutes. And this is our P of X. Okay, so X could be anything between 0 and what? 60, because we're going from 10 to 11, so 60 minutes. Alright, and I could put a tick mark for every single one there. How would I find the probability of each individual minute? So we know the total probability is 1. And how big is our interval? 60. So the probability of them coming at any given time is 1 over 60, because it said everything was equally likely. Okay, and you could draw like little rectangles, but it said it was uniform. Everything had the exact same probability. So if I looked at this, my uniform distribution just gives me a rectangle. No matter where I'm at in that, no matter what x value I pick, my probability is 1 out of 60 because it said every minute in that interval was equally likely. Any questions there? Let's look at some questions about this. So find the probability of choosing a time between 15 and 30 minutes. So if it's between 15 and 30, that's a total of 15 minutes, right? So essentially I'm saying on this graph, if I want to be between 15 and 30, what's the probability? And you could essentially be anywhere in here. So the probability is just that area. How do you find the area of a rectangle? Length times width. So the width of it is 15, and the height of that rectangle is, so we get 15 over 60 or 1/4. So there's a 25% chance that they will be there between 15 and 30 minutes. B, there is a 30% chance your package will arrive within the next blank minutes. So think about how we find this probability. We take the length, and we don't know on this one, so the x, times the height, our probability is 1 over 60. And I get a 30% chance. So how would you solve that? Multiply by 60 or divide by 1 over 60, and what do you get? 18. So there would be a 30% chance the package comes anytime in the next 18 minutes. Right. So uniform distributions, the nice thing is everything has the same probability in there. So it's just like probability is just finding the area of a rectangle. Let's look at this next. Any questions on this one? All right. We have talked about shapes of graphs before. We know we can have like bell-shaped or symmetric. We can have skewed left, skewed right. Anything that is symmetric or bell-shaped is called the normal curve. So the shape is really important here. And this one, those rectangles are representing the different probabilities. If I used more rectangles, do you think it would be more or less like a perfect curve? More. The more rectangles you have, the smoother your curve would be, right? So if we want our data to be normal, we need a decent amount of it. If I don't have very many, then it's going to look more choppy and less bell-shaped. So to actually treat it as a normal distribution, we will have to have enough data to make it that way. And we will talk a lot in the coming chapters about how much do we need to make it normal and those kinds of things. So when we are talking about data, we can say it's normally distributed, or we have a normal probability distribution. If the relative frequency histogram, so the graph of your relative frequencies, is the normal curve or the bell-shaped symmetric graph. we kind of talked about this more when we did like empirical rule. We know like the mean is the middle, and you could have plus and minus the standard deviation, so you kind of see that nice smooth curve there. And in fact, the empirical rule, remember, only worked for bell-shaped symmetric data, so it applies to our normal distribution. When we're talking about our normal distribution, it is always centered at the mean, so it's symmetric. So that means half the data is above the mean, half the data is below. Since it's symmetric, the mean, median, and mode are all going to be your same point, because remember we talked about like when data was skewed, that's what made the mean and median different. When we had bell-shaped data, the mean and median were the same. Inflection points, we'll talk more about those later on, but that's basically one standard deviation away. Total area under the curve is 1, half above, half below, and we can use the empirical rule because it's bell-shaped. And here's your refresher. We've had that empirical rule before. Remember, 68% was within 1 standard deviation, so half above and half below. 95% within 2 standard deviations, 99.7 within 3. So let's just try looking at a graph and seeing if we can pick out some information. Would this be a normal curve? Yeah, that looks pretty normal to me. Nice and symmetric. All right. What would be the mean? 2, the center. And the standard deviation. So the mean is the center. In a normal curve, remember this is 1 total standard deviation away. So we are looking, how far is it from the center out to that first standard deviation? 3. From 2 to 5 is 3. From -1 to 2 is 3. So a standard deviation here is 3. Any questions on how we got that? Take a second and read this question and see if you can figure out which is which. They both have a mean of 10, which makes sense. They kind of peak at the same. One of them has a standard deviation of 3, and one has a standard deviation of 2. We're trying to figure out which is which. Remember, standard deviation is how far it is from the center to essentially where your graph kind of switches direction, when it kind of curves out like that. We could also think a bigger standard deviation would do what to your graph? Make it wider, okay? And that would stretch it, basically it's going to get wider and shorter. So the bigger standard deviation would have to be B because it's shorter and wider. The smaller standard deviation would have to be A. Did you guys get that? When we are talking about the area under the normal curve, there's a couple different ways it could be interpreted. We can think of it as a proportion of the population with a certain characteristic. So if I were looking at a normal curve for baby weights, okay, newborn weights, then I could look at the height of the curve at a given weight, and that percentage would be like the proportion. So if I had a 12.5%, I could say, 12.5% of the babies weigh this much or less. We could also think of it as a probability that something would occur. So let's look at an example and try to write those sentences of what it might be. So the weights of giraffes are approximately normally distributed with a mean equal to 2,200 pounds and a standard deviation of 200 pounds. So if you think about your normal curve, so we know it's bell-shaped. Hopefully you can draw a halfway decent bell-shaped curve. Okay, the mean was 2200. Standard deviation of 200, so that's like saying, you know, one standard deviation would be here and here. So, that's part A. We labeled everything. Part B is shade the area under the normal curve to the left of 2,100 pounds. So a lot of times when we talk about the normal distribution, we'll be finding the probability that it's below something. So 2,100 would be here. So to the left of it would be this part of my curve. Okay, so if I told you that that area was 0.3085, I want to write the two possible interpretations for that. So one of them is to think of it as a proportion with that characteristic. So the proportion of giraffes weighing, this would be 2,100 pounds or less, right? Because we shaded everything below that, is 0.3085. So essentially treating that as describing the population, describing all the giraffes. So a little under 31% of my giraffes weigh under 2,100 pounds. The second is to think of it as a probability. So the probability, a given giraffe weighs under 2,100 pounds is 0.3085. So one interpretation is to describe that population as a whole. The other is to think of it as a probability for one given giraffe. Any questions for me there? So tomorrow we will actually start finding the probabilities with these. Today we're really just talking about what a normal distribution looks like and that uniform distribution. So we will go over the tests shortly, but I'm going to go ahead and give you the homework. So how I'm going to do it is I won't collect this until we are done with the chapter. This is the chapter 7 homework. So tomorrow we'll cover 7 and 2, and then I'll probably give you class time on Wednesday to kind of review and work on it as well. So I probably won't actually collect this packet until Monday, but you'll probably have it done before then. Today's portion isn't too long.